So with apologies to our host, I have the Gartner Emerging Technologies Hype Cycle. And as you can see, cloud computing is one of those things that is at the peak of inflated expectations. Cloud computing will solve every problem known to man. The purpose of my talk today is to shove us down to the curve. First, I'm going to take you into the valley of disillusionment about what really happens with cloud computing. And then I will hopefully move you into the slope of enlightenment as we talk about really where HPC and cloud computing can work together. So what I want to start with is talking about some of the common assertions that are made about cloud computing, and then what we've discovered in the course of our research with the Magellan Project. The first assertion is that cloud computing is really simple to use, and if you start using clouds, well, you're not going to need to have all that infrastructure and the people that you need to actually run it. Yes, it's true you'll save on the infrastructure, but you still do require the system administrators. One of the things we did with Magellan is we set up a cloud computing infrastructure using Eucalyptus and invited a number of research projects to come in and attempt to take their applications, which were on standard environments, and move it into the cloud. Well, what we found was that the infrastructure as a service kinds of clouds required an enormous amount of system administration expertise. So we were able to get a number of projects from high performance computing and from biology and so forth working on the cloud, but it took the scientists working together with our experienced cluster administrators to actually make it work. One of the things which was very clear is you had to take the images that were going to run, and they had to be customized for the application. This is necessary to get both the right kinds of applications, also to trim down the image in order so that you would have just the software you needed. Many of the cloud deployments do things like doing diskless provisioning, so you end up with a RAM disk inside of your memory that's taking up that's holding the image, and you want to trim that down for the particular application. And that takes a lot of work and a lot of experience to do. You also find that sort of right off the truck, if you have a Linux, which is pretty easy to get up, you don't have things like batch environments. I know Amazon is doing some stuff in terms of customized images to make that more useful. But what we found even more tricky was that if you wanted to take advantage of the large parallel file systems that we had available on the Magellan project, that was a much more tricky problem to get embedded in the image and to get it working. Another thing that users don't really think too hard about when they put together an image to run is the whole question of security for the image. And that, again, is something that relies on a lot of expertise to do properly. There are a lot of tricks. There are some things that we do within our center, for instance, to do an instrumented SSHD that allows us to watch over users that someone might not just naturally go off and install. So in the end, we found that there was an awful lot of work here that in essence was trying to take the scientists who wanted to get their job done and try and turn them into system administrators. Another misconception is that your job will run immediately within the cloud. We did a number of studies to just say, what would it take to actually marshal a fairly modest-sized cloud, even up to like 100 nodes. And you could get a fair degree of variance in terms of the time that it would take. Sometimes it would be really quick, sometimes it could take an hour, sometimes we'd actually never succeed. I've actually heard this from some other friends who do work in CFD that have had difficulty getting relatively large numbers of nodes in a commercial cloud. But one of the things that we did was we went back and looked at the scheduling parameters for Franklin, which is our 350 teraflop Cray system, and asked how many cores would we actually need at any given time in order to provide essentially instantaneous access to the machine. And these are basically the number of cores requested in, I believe it's half-hour time slots for about a 15-month period. And you can see there's very high variance. And unfortunately, actually, there's a problem with the graph here, and it clipped off the peaks. The highest peak there is actually 400,000 cores. So what we find, if in order to be able to provide instantaneous access to a cloud, especially for people who are doing lots of core-intensive work, you need to have a lot of residual capacity that's available to you. If you need 1 or 2 images launched into a cloud, that's probably rounding error compared to the available utilization in the cloud. But if you're looking for 10, 100, 1,000 different cores at any one time, that's difficult to achieve. The other assertion is that clouds are a more efficient way of doing computing. Well, we went off and we did a fair amount of research and experimentation in terms of running different applications across a number of machines. You see here, we've listed a couple of machines. Carver is a recent vintage InfiniBand cluster. Franklin is our 40,000 core Cray that's about 5 years old. Laurentium, which is a mid-range cluster at Berkeley. Amazon Cluster Compute, which is a specialized HPC-oriented version of the Amazon cloud, and then Amazon EC2. And you can see sort of the off-the-shelf EC2 images ran much more slowly than anything else that we could have available. The cluster compute service from Amazon did pretty well, or was a lot closer to what we could do with a modern vintage bare metal InfiniBand cluster. And the codes here, some of them you'll recognize, they're the codes that we use for procuring large systems. These are 2 more codes here. The scale has changed. It's increased by about 4x, so there are some codes that get even as much as 50 times slower if you run in sort of a simple-minded cloud image. And then we also tried to look at what happens with respect to the interconnect. Virtually all of the clouds are essentially web infrastructure repurposed for HPC or cloud-based applications. We've been, with the Magellan project, we had InfiniBand-based clusters. And the number 1 unity on this graph is essentially what would happen if you run with native InfiniBand. So we looked at various other things. We ran TCP over IB, which gave us something in the neighborhood of 25 gigabits a second. We had TCP over gigabit Ethernet, and you can see what happens there. And then Amazon CC, which is a 10 gigabit network. And you can see that the scaling falls off using basically the Ethernet-based protocols underneath the high-performance computing. Now, it's interesting to say that recently we've been doing some experiments using Juniper's QFabric together with Mellanox's Ethernet adapters running Rocky, and we're actually getting pretty good performance for that. So we hold out a fair amount of hope for those, and that seems to be getting closer to the unity on this graph. There are some other assumptions that are made for clouds. Now, again, from the Federal Computing Cloud Computing Survey, there are a number of assertions. Number 1 is that you can get much improved utilization. What they say is that in a study of federal data centers, that typical utilization was about 30 to 40%. That's true for doing sort of commercial business IT, but is it true for HPC? I think you know it's not. And the other is that commercial data centers tend not to run very close to the bleeding edge of technology and hence suffer from efficiency. Well, with HPC centers, we know that's a lot different. I mean, our center, other centers run greater than 90% utilization, so there's not that much to be had in terms of improved efficiency from trying to use the leftover capacity. And it's certainly the case that HPC centers tend to partner with vendors to field leading edge systems and are much more aggressive with it, taking on the technical risk. Another issue is you look at it, the computational needs. If you're looking at a business application, the computing requirements are pretty much bounded. You have a certain amount of transactions that you do per day. Yes, it may change from middle of summer to the Christmas rush. But if you gave a typical business free computing, would they be able to take advantage of it? Probably not. But we know for a fact that when we give out free computing on our systems, we can get extraordinarily high usage. We demonstrated that when we brought our Hopper system, which is a petaflop cray online. And before we got through acceptance, we were giving out free time. During that period of time, we were running more applications at very near the capacity of the machine, 130 to 150,000 cores, than we will probably see in the lifetime of the machine. And the other thing is, you look at enterprise IT, it's essentially a scale-in approach. That is, the issue that you have is trying to consolidate multiple applications on a single machine. In HPC, it's a very much different problem. What we're trying to do is to use many machines to solve a single problem, so we're scaling out. Another assertion that's quite common is that by using clouds and using the purchasing power of the commercial cloud provider, is that you're able to ride Moore's Law without much additional investment. Well, we went and pulled a study off of the web that looked at the price trends, and this is essentially a standard cloud instance looking back over the last 4 years. And it's only dropped about 18%, although over that period of time, the number of cores that have become available from Intel or AMD have increased anywhere from about 2 to 5x. So what it says is that technology is not driving at least the cost of the cloud services today. It should drop over time, but it is more driven by the business needs of the organizations, the cloud providers, and the supply and demand curve for the cloud computing. And the last one is that commercial clouds are much cheaper to operate than your own system. Well, you know, we tried real hard to get a handle on that, and we've looked at it a number of different ways. And as we reported that to different people, the question was, well, did you include this? Did you include that? So we decided to go and figure out what it would cost us to run NERSC by buying the time from Amazon. And this is the way it broke down. So this year we'll be serving up about 1.4 billion hours of CPU time. And if we bought an appropriate number of systems using reserved instances and the larger memory systems, it would take us something in excess of $180 million to do so. Now, our budget is only $55 million. And that includes not just the computer time, but it also includes consultants, security consultants. So, you know, this alone is about 4x our budget. And probably if you look at the actual cost of the machines, it's probably somewhere closer to 8 times the budget of NERSC. And when you look at the more microscopic views of the costs on a core-to-core basis, those kind of ratios are borne out. So that's the trough of disillusionment. There are the hype isn't necessarily what it says, but then where would you actually use commercial clouds, and where are they effective? So here's what we've seen where it's been effective for the scientific users. Number one is if you have projects that have relatively high burst needs, it's a really good thing because you can avoid procuring, say, a mid-range system and leaving it idle most of the time. And you can certainly have access to a much larger scale than you would otherwise be able to afford. Another area that has proven to be particularly effective is we call it sort of high throughput computing, high throughput applications that have relatively modest data needs, because if you have high data needs, the cost economics change substantially. Very good examples of that is in the bioinformatics area. Another area is the question about infrastructure challenge sites. If you cannot, I mean, most sites today, as we are starting to scale up and put in machines, their number one concern is probably around power. Second one is around cooling, which is essentially the same thing. And you know, at some point you hit the wall. And if you hit the wall, then the cost of expanding the facility may be much greater than the IT cost of going outsourcing to the cloud if you have a long-term steady use. But you still need to look at the long-term cost of that and make sure that the lifetime of the application and whether or not it's going to make sense for you. And then the last one, which is I think is probably one of the more important ones and is understated, is if you don't know what the computational profile of your application is, the best thing to do is to buy a little bit of time in a commercial cloud and go out and understand it before you try and deploy it. So the last question I'd ask is, if you look at this, it at least says that for HPC, maybe the centers are a good way to continue to use. But is an HPC center really a cloud? NIST has a definition of clouds. It says, you know, you have to be able to pool resources. You have remote access over the networks. You measure the service. You have rapid elasticity, and you have on-demand self-service. Well, in HPC centers, we certainly have resource pooling. We've been doing that since time immemorial. We have very good network access. All of the large centers are tiered with peer with multiple providers. They have high-speed networks. We do measure the service. We give allocations and so forth. You can pay as you go, although the coin typically may be an allocation from a government agency rather than actual dollars. The area where it's really different is this whole notion of on-demand self-service. And it's something that we have somewhat struggled with, is you can't really get more than your allocation allows. And more importantly, you don't necessarily get it right away. I sort of knocked clouds for the point that you can't get relatively large clusters set up easily, but it's certainly the case that in centers, the most frequent complaint that we get from users is that the queue waits are looking like 2, 3 days, maybe even a week in some cases, for certain kinds of jobs. So that's really where we kind of look at what we can do. What we've been trying to look at from our center is what we can do differently in terms of that last aspect of it. And we've been working with some of the scheduling providers to look at alternative ways and effective ways of scheduling things to give the impression for the smaller jobs, the ones that need more rapid turnaround, the image of having on-demand access. But it is fundamentally, it's a business question, because it's all about a business model. It's not really a technology. It can be applied to centers. The only question about achieving on-demand elasticity is whether or not you either have idle hardware, which we do not want to have, whether or not you can share cores or nodes, and that has a performance cost. And then the last question is around scheduling policies, which is the area that we're working at, and looking at either preemption, special kinds of short-term queues, or discount strategies that allow for this to happen effectively. So, closing remarks, our belief is that cloud computing as it exists today is not really ready for HPC. There are some early signs, such as the Amazon Compute Cluster. but it's certainly the case that the HPC resource providers can learn from the cloud. As I say, we can learn about the instances. We're also experimenting with the concept of having images loaded on demand through the batch scheduler so that we can customize the software load to particular applications and so forth. Any questions?
If hypothetically, if that Amazon ratio was reversed, would you guys be moving in a different direction, do you think?
I think we would be very much asked to look in another direction. Steve?
Yeah, Jeff, so just as you don't pay full price for your computer hardware, is it possible that if you bought that many hours from Amazon that you would be able to negotiate an alternate price? And do you have a ballpark of what that might be?
Certainly. I mean, this analysis is based on retail pricing. And maybe Deepak could comment on how deep a discount we could get. But we've thought about that, and we've looked at gross margin issues. And it's really hard to make up a difference of a factor of 4x in terms of the cost between what we'd be able to buy in, sort of off the shelf in the commercial environment and what we're able to do. I mean, understand, you know, the centers are really big consumers. We're customized to our particular applications. We have, you know, pretty good buying power, not as good as the mega data centers, but it's not too far off.
In the mid to late 90s, there were a number of commercial HPC centers that sprouted up based on the thought of, you know, you might have demand for it, and almost all of them died out, and only the government-sponsored ones remain today. Is cloud just the latest installment of that cycle?
I'm not quite sure how to respond to that. I mean,
I just want your view.
You know,
I'd like to know.
Like most you know, technologies or concepts, I think, you know, cloud is the latest label that's put on, you know, a way of doing business, right? You know, if you go back farther, it was called time sharing, right? I'm showing how old I am. Yeah. And, you know, going forward, it's going to be different. I mean, another interesting question, I think, is, you know, we've been talking about exascale machines here. And, you know, if we get exascale machines, you know, are they going to be a way of delivering clouds? You know, we all know, right, that one of the most important premises of the exascale program is it can't be a one-off, right? And if you look at it, the design point for an exascale machine, yes, you know, it's a quadrillion operations a second, but if you look at a single rack, it's about, what, 50,000 cores, 5 to 10 petaflops, maybe about $1 million or $2. That's a pretty hefty machine that you could put in any given center. It also runs at about 100 kilowatts. And, you know, one of the things that all the mega data centers need is the ability to reduce their power load, because you know, it's an enormous design point for them. And I think, you know, if we get to that, the kind of power levels that we're going to get to with exascale, and if we're not quite so flop heavy in it, I mean, if we kind of back away from the SIMD and more into the mini core thing, you know, these kinds of machines can be used for, you know, web services, certainly data analytics and so forth, that, you know, are properly the kinds of thing that we may well see in the cloud. And secondly, you know, we'll be able to look at, you know, running capacity jobs within these same classes of machines. I mean, there's a lot of good science that's going to happen at exascale, but there's also a lot of good science that's going to happen at much smaller levels, and we'll be able to run more of it. And whether or not it's cloud or batch or whatever, I think there's a lot that's to be said as we go through this next decade in terms of our capability to apply these technologies to it.